Okay. Okay. Welcome everyone again to another installment of this CTMP seminar series. Today, we're delighted to be joined by Sören Schlichting, who is currently a full professor at Bielefeld University in Germany, and is a leading expert in high-energy QCD. He completed his PhD in Heidelberg University, and worked as a postdoc at Brookhaven National Lab. Was a Goldhaber Distinguished Fellow, and held the position of research assistant professor at the University of Washington. And I think when he was on his way out, I was on my way in as a postdoc. So our times overlapped for about, I don't know, a couple of weeks. So,
During COVID?
No, before COVID.
Oh, okay.
Yeah, in any case, he then moved on to Bielefeld to be a junior, and now is a full professor. Okay. So he is, I learned, a recent recipient of the Zimanyi Medal awarded by the Hungarian Academy of Sciences. His interests, amongst others, in the early dynamics of heavy ion collisions and small x physics. So he's in good company here, and also, non-equilibrium dynamics. Right. So we are very happy and excited to have him here today to speak to us about the basics of heavy ion collisions. Oh, sorry, basics of collectivity in heavy ion collisions. All right. So, Sören, please take it away.
Yeah, thanks a lot for first of all, for the invitation and also the very nice introduction. So indeed, so as Marwande said, so today I'm kind of so the plan for today was kind of introducing sort of the basics and the framework of heavy ion collisions, and then next week I will sort of dive into the details of new aspects of non-equilibrium dynamics in heavy ion collisions. So so a lot of this will be sort of introductory and basic. So for those who already know, never underestimate the joy of learning something that about something that you already know, right? And then for those who don't know, I mean, also feel free to ask questions at any time, right? So I'd rather make this interactive and not cover everything I prepared than sort of losing you in between. Okay. Good. Okay. So let me start out. So this is going to be about heavy ion collisions. Okay, so let's start why we care about this at all. So why should we collide heavy ions? What do we want to learn? Okay, and so kind of if you think about the really big picture, okay, then we want to understand sort of the stuff we are made up of. So understanding fundamental constituents of matter. Okay, so if we look at sort of matter as we know it, let's say a balloon which is filled with helium, right? And there's the helium atom. Okay, the atom is an outer electron shell. Then there's the nucleus inside. Unfortunately, I can't point somehow. So okay, well, I guess you'll be able to catch on. So the nucleus itself is some of bound of protons and neutrons. Okay. And but these are themselves also composite objects which are made out of quarks and gluons. Okay, and so what we do in high energy physics is, of course, we want to break down things to their most elementary constituents and sort of understand how they build different structures and how they emerge. Okay, and so for our best knowledge that we have today is that these quarks and gluons are really truly fundamental objects in nature. Okay, they could well be, and so we want to understand how they interact, how they work together, how they organize themselves into different structures. Okay. There's a theory for that. Okay, and the theory for that is the theory of strong interactions. So this is the interaction between quarks and gluons. Okay, and at the fundamental level, it's actually relatively simple. It doesn't look very, very different than for instance, quantum electrodynamics would look like. So we have bosonic degrees of freedom. These are the gluons. So this is kind of the QCD analog of the photon. Okay, and then there's the QCD analog of the electron, which are the quarks. So these are fermions. Okay, and they interact with each other. What makes the theory different from electrodynamics also is that the gluon actually also interacts with itself. Okay, and this gives rise to a number of very interesting and very non-trivial features. Okay, so I said, okay, we know at the core everything is quarks and gluons. Okay, but yet it is such that we don't see them in nature, and there's a good reason for that. Okay, The reason is that the strong interaction actually is strong, and it is so strong due to the self-interactions of gluons that actually these quarks and gluons under normal conditions, they're always bound together into hadrons, so into bound states, okay? And these are particles as we know it, like the proton, the neutron, but also others like pions and kaons, okay? And this phenomenon is called confinement, okay? So under normal conditions, we don't see quarks and gluons, we see bound objects, okay? And also the strong interaction actually gives rise to kind of dynamic mass generation. So in a sense, you can think of this, that the interaction energy in the strong energy is actually large, and that's actually what determines a large part of the mass of, say a nucleon. Okay, so well, okay, good. This means it's actually not so. So if we actually want to learn about QCD, it's, you know, about quarks and gluons, that's actually not so easy, right? Because normally these things are somehow inside bound states, okay? So how can we go about really exploring this? Well, in principle, you have two possibilities, right? Either you really look very precisely inside the bound state. This is something you would do in scattering experiments. So you would use use, for instance, deep inelastic scattering, so not optical light but electron beams to probe this to have a better resolution, and then you can kind of look in there, okay? But sort of an alternative way you could go and think about this is that you try to dissolve the bound state somehow, okay? And in order to achieve that, what you have to do is you basically have to take nuclear matter, so protons and neutrons, okay? And you either have to heat them to very high temperatures, okay, or you have to pack them extremely densely together, okay? And this is kind of sketched here in the middle of this of this slide. I mean, sorry, I'm really confused. I don't have my mouse here. I want to get my mouse so I can point to you. Let's try this whole thing again. How do I play? Okay. Okay, now you see the slides on. Is that okay from the view? No, not really. No. I should wait. There's so much Zoom stuff here that I don't see my mouse. Okay, good. No. Okay, let's keep going like this. Okay, so you take these bound states, and if you heat the system up, then essentially what will happen is that more and more particles will show up until at some point they are very densely packed. And if they're very densely packed, then essentially the idea is that sort of individual constituents, they no longer know which bound state they belong to, and sort of the whole thing reorganizes into some kind of soup where quarks and gluons can roam around more freely and kind of move from one object to the other. And this is this is then a state where quarks and gluons really appear in their natural form, okay? And that's what we call the quark-gluon plasma. And so the basic idea of heavy ion collisions is to actually achieve these environments, okay, where we can really concentrate such a large amount of energy into a small volume. Well, it's on QCD scales would be a large volume, and thereby realize the conditions where quarks and gluons are no longer subject to confinement. Okay, so how do we know when this happens? So for this, we have to, we can go to thermodynamics, okay, and we can ask, the theoretical question of when does this occur? What temperatures do I actually need? Okay, and for this, there's the comfortable situation that in principle we can take this theory that I showed. So take the theory of QCD, simulate it on a computer, okay, and just calculate what that temperature is, okay. And so this is essentially shown here on the right panel. So what you take is you take the theory and you solve it on a computer, and you basically calculate the thermodynamic partition function, Okay, from this you can calculate, just as you do in statistical mechanics, energy density, pressure, entropy density. Okay, and you can plot this as a function of the temperature. Now, if you normally look what the energy density of a relativistic system is, then that's written here on the left. Okay, it's some factor times t to the 4, and that factor tells you tells you how many degrees of freedom there are in the system. Now you can think about when you only have the possibility to pack things into bound states, okay, then that's fewer degrees of freedom than if they can roam around freely, okay. So what you should see is that around the temperature when this deconfinement happens, is that there's an increase in the number of degrees of freedom, and that's actually what's plotted here on the right. So it's the energy density divided by t to the 4, okay. So it gives you kind of the effective number of degrees of freedom. And you see this strong rise around temperatures here marked in this yellow region, okay, around temperatures of about 155 MeV, okay. So at this temperature, you see a large rise in the effective number of degrees of freedom, and that we take as an indication for the transition from bound hadronic states to actually a quark-gluon plasma. Now, what is that temperature? So that temperature is actually extremely hot, okay? So it's more than 1,000,000 times the temperature of the sun, about 10 to the 12 Kelvin, okay? And so it's not really that easy to achieve this, okay? And yeah, so what do I want to say here? Now, in fact, temperature is not the only handle you can play. In fact, you can ask yourself, okay, sort of what are other things you can deal with? I said so you can either heat the system up or you can compress it, okay? And you can do this first principle calculation sort of in a limited range. Temperature is easy, compression is hard, okay? And you can convince yourself that, okay, at low temperatures and low density, you have the normal bound phase. This is what's called a hadron gas here. Okay, and at high temperatures and high density, so moving up and moving to the top right, okay, that's where the bound states are dissolved and one enters the phase of a quark-gluon plasma. Yeah? And so, in addition to this transition line that's somehow indicated here, you also see these bangs along with trajectories, and that corresponds to conditions that you can reach in heavy ion collision experiments by varying the collision energy with which these ions collide. Okay, and so what this is supposed to signify is that if you study heavy ion collisions at different energies, then what you actually do is you explore sort of different regions in this phase diagram of strong interaction matter. Okay, and you can actually reach temperatures which are high enough to probe this new phase, the quark-gluon plasma. Okay, so how does a heavy ion collision work? Let's actually go here. Okay, so what one does is one takes heavy nuclei such as gold or lead or uranium. In principle, one can also do this with lighter nuclei. Then one sort of physics is a little bit different. I'll say more about this next week. Okay, and what you do with them is you accelerate them to very, very high energies. For this, you need gigantic accelerator facilities. So on the left, there's a picture of the relativistic heavy ion collider. That's in Brookhaven, US, and right is the Large Hadron Collider. So you have these kilometer-long rings, okay? And you can accelerate them to energies which we quote this center of mass energy. So at the case of RIC, this would be 200 giga-electron volt, and in the case of the LHC, this would be up to 5 tera-electron volt. Now, what does that mean? So what is this center of mass energy? Well, it's the sum of the 4 momenta of the 2 colliding nuclei. Okay, so in the rest frame, this would basically be twice the mass times the boost factor that you reach, so the Lorentz boost factor that you reach. Now the mass of an individual nucleon is about a GeV. So what it means is that in the case of RIC, you reach boost factors of about 100. Okay, so the thing is, for instance, about 100 times Lorentz contracted. And in the case of LHC, this goes up to thousands. Okay, so these are really truly highly relativistic collisions of these nuclei. Now, how does this look like in practice? So this is a nice movie from the LHC. So what you have is you have different stages of accelerators. You create two bunches of these beams. Okay. The beams then go into some other accelerator where the energy is ramped up, and then you have these two counter-circulating beams in the main accelerator. So this is then the LHC. Okay, this is a view of how this looks like. You have the tunnel. You have a high vacuum beam pipe in here. There should also be magnets around which bend the beam so that it stays on this circular trajectory. And then inside this you have either protons or nuclei, which move through the beam, and then there are these interaction points where they steer the beam onto each other. That's where they collide, okay? And that's also where you have gigantic detectors that measure everything, okay? And then when they collide, what actually happens is that they produce a plethora of new particles, okay? That you can then measure and analyze in the experiments. Oh, whoop! I did something dump again. Okay, so all in all, okay, so you have this relatively sophisticated experiments, but in practice you have very limited control over actually what happens in this. In fact, you cannot really steer the beam very well. So the only things you really actually control are sort of what is the species of nuclei that you collide, and what is the center of mass energy, or so what's the energy at which you collide this. You can observe a lot of things. You can measure all the particles that are produced. This can be hadrons. This can also be just electromagnetic radiation, so photons, electrons, anything, okay? But you cannot really watch this as a movie like we did, okay? But you can only measure at the very end. Yeah. So to really make sense of this, what you have to understand is sort of the whole dynamics of the reaction that is going on, okay? And then really to make conclusions about, you know, how the quarks and gluons that were existing at some stage of this actually behave. Yeah? And so that's kind of the whole game of heavy ion physics, really trying to understand the dynamics that goes on in this reaction. Okay. So what you actually measure at the end of the day is you measure the particles that are produced in the reaction. So here's an example from a collision event at RIC. So on the left, you would see the beam kind of going in and out of the screen here. On the right, you would look onto the side. So the beam would go through like this. Okay, and each line that you see here is a particle that is produced that you see in this detector. So you can look at it. So this is one individual collision. Another one looks different, and so okay, good. The question is, how do I learn something about the strong interactions from just looking at these pictures, right? And that's indeed very non-trivial. So the first thing you want to do is I'll talk a little bit about sort of the phenomenology. What are the things you can measure? What are the phenomena you observe? Okay. And the first thing you can ask yourself is, well, how does it come that here there's so many produced and here there's so few produced? Okay. This looks much denser than this, so much more particles than here. And well, there's a very simple explanation for that. Okay. And so when these two ions collide, you cannot actually steer the beam to the precision of of the size of an individual nucleus. So what happens actually is you have huge bunches of particles on both sides, and you actually just hope that some of them will collide. But they can collide here like with some finite impact parameter, like shown on the left, so with some finite displacements, or they can basically collide head on. Okay, and you have no control over that. So what you do in practice is you basically just you of course expect that when they collide more head on, that they produce more particles. Okay, and so what you do is you actually classify events by how many particles they produce. So you basically may just make a histogram of all the events as a function of how many particles come out, and then you group them into so-called into classes of percentage. So the top 1% that produce the most particles would be called what we call the 0 to 1% centrality class. Okay, and so these ones we expect to be very head-on. Yeah, but then if you go to events which produce few particles, this typically happens when they're very much side to side. Okay, and this would correspond to what we call more peripheral collisions. Now, this is simply counting how many particles come out. Of course, there's more information in all these measurements. The next thing you can do is you can kind of measure the momenta. Okay, and so clearly there's an asymmetry here in the way that you do this. So on the one side you have the beam. Okay, so the beam comes in from a certain direction, okay? And that's what we call the longitudinal direction. And then the plane transverse to this direction is what we refer to as the transverse plane, okay? And so what you can measure in the experiments is you can measure basically the energy and the momenta of the produced particles, okay? And that's in principle fine. However, because there's this strong asymmetry, in particular, we have this highly relativistic motion along the longitudinal direction, it is advantageous to actually not just use energy and momenta to parameterize the momentum of the particles, but it's useful to distinguish between the momentum in the transverse direction and the one that's in the longitudinal direction, okay? And so what one uses to denote the momentum in the longitudinal direction is what is called the rapidity. So one actually uses a combination of the energy and the momentum, like is written on the bottom left here, okay? And for massless particles, this actually just essentially corresponds to the angle under which, the hyperbolic angle rather, under which these particles come out. So in the figure here, you see how at different angles the different rapidities come. Now, why is this advantageous? This is advantageous because what happens is that this parametrization is very efficient when you do a Lorentz boost of your system along the longitudinal direction. And what you can argue is, I told you that, okay, at the typical collision energies that we study, okay, the system is already highly boosted. I mean, the gamma factors were hundreds to thousands, the Lorentz gamma factors, okay? So if I just boost the system a little bit, this will not have a big effect. I mean, it will essentially not change very much. And so if I perform a boost along the longitudinal direction, then basically what happens is that this rapidity coordinate, y, okay, is simply additive under such a boost. So you can, if you want, you can work this out in your free time, okay? And so that is beneficial because this is sort of an approximate symmetry of the system. And indeed, if you study this in experiments, so at low energies, of course, the beam only has a small rapidity. Okay, at high energies, this is something like order 10. Okay, and if to order 10 I add order 1, that's a small effect. Okay, and indeed that's what you see in the measurements that you perform. So here again, one is counting. So in this plot, one is again counting the number of particles that are being produced as a function of now the rapidity, or actually pseudo rapidity, which is very closely related. Okay, and what you can see is if you look somewhere in the center, so in this blue striped region, okay, then you can see that for all of the curves that are shown here, this is very flat around the center, reflecting the fact that sort of a small boost of the system doesn't really change things very much here. Okay. Now, of course, if you move closer to the beam, then it does make a difference whether sort of you missed the collision or not, and so that's kind of why this goes down. Okay. The other information that you can take from these measurements is that actually there's a large number of particles produced in the collisions where in this case, xenon nuclei hit very centrally. So in the center, you have per unit rapidity more than 1,000 particles that are produced, okay? And then, of course, for the more central collisions, you produce more than you do for the more peripheral, but that's kind of how you define things in the first place. Okay. What else can we learn, or how can we actually connect this to properties of the QCD phase diagram that we want to study? And what we can also analyze is not only sort of, so we said how many, right? How do they move? Okay, now we can also ask ourselves what type of particles actually come out. Okay, and that's sort of so there's a very kind of interesting behavior that one finds there, namely, so if you think about, you have a system, let's assume very simply, you have a thermal system, okay? You can ask yourself, how abundant is every particle in that system? So if you just calculate the number of particles in the thermal system, what do you have to do? Well, you have to take the thermal distribution function. So if these are bosons, you take the Bose-Einstein distributions. If they're fermions, you take the Fermi-Dirac distribution, okay? You integrate this over the energies, and you get how many particles are there, right? So each particle is weighted with the energy over the temperature. If there's some chemical potentials, you also have to weight them with their charges, okay? And then there's an overall degeneracy factor for spin. Yeah? Okay, so you can calculate this, okay, in just an equilibrium system, okay? And you can compare this with the actual measurement that you do in heavy ion collisions. So in heavy ion collisions, you identify what particles come out. There are all kinds of QCD bound states, pions, kaons, protons, and so forth, even nuclei that you can produce in these collisions. And what you find is that somewhat surprisingly, okay, you have this crazy reaction dynamics. What you find at the end is everything is actually very well described in terms of just a thermal distribution. So this would be this blue line here, okay? Now, if you correct in addition for the fact that some particles decay into others, then you expect a little bit more of some and a little bit less of others. So that then gives rise to this blue bars, okay? And from this, for each collision, or for each collision energy, you can actually attach a temperature and a chemical potential that you reached at the stage where really the particles were produced in these collisions. Okay, and so this then really allows you to kind of make a connection that I was sort of trying to highlight before, between a heavy ion collision and sort of different points in the phase diagram of matter, so of QCD matter. Okay, yeah, and that's essentially what gives rise to the endpoint of these different trajectories. Okay, so on the left you see again kind of the same phase diagram. Okay, but now with points that have actually been extracted from studying heavy ion collisions at different energies. So if you're at the highest center of mass energies, then you reach the highest temperatures, but lower chemical potential. Okay, so this would be the points on the far left here, and then at lower energies, one reaches somewhat higher density but lower temperatures. Yeah, and so the temperatures you can extract, you can compare with this kind of theoretical calculation of when do hadrons cease to exist and when do they become this plasma of quarks and gluons, okay? And what you learned is that the temperatures and densities that you reach at least earlier in the collision, when everything was sort of still compressed, are actually higher. And so by this, we know that heavy ion collisions actually provide us access really to this new phase of matter, the quark gluon. Okay. Now, what else can you learn? And so this is now kind of coming more to really what I will then also talk about next week. Okay. Another very interesting observation that you can make is you can now ask about sort of, if I analyze all the particles that are being produced, okay, what are their properties? Yeah? So where do they fly off essentially? Yeah? And well, naively you may expect, okay, they just randomly fly off in all kinds of directions, okay, and to some extent that's actually true, okay. But what you will find is that if you look in the plane perpendicular to the beam, so in the transverse plane, and there you kind of make a histogram as a function of the angle around that beam, so the azimuthal angle, okay? What you will find is that in each event, there will be these very pronounced modulations that you see here in this right plot. So these are order 10% modulations, okay? And so that's much larger than just sort of an average statistical fluctuation, yeah? What you find is that, so you find this kind of 10% modulation, and of course this is just some modulation in the angle. So what you can do is you can decompose this into a Fourier series, right? So every function is periodic on 2 pi, you can decompose into a Fourier series with some Fourier coefficients. So these we call Vn, okay? This in the IBI communities is called the flow coefficients, okay? And it turns out that in principle you can do this for every magnitude of the momentum, but it doesn't actually matter what's the magnitude of the momentum. Very weakly depends on this. They really seem to care about sort of a common direction or common preferred directions that they like to fly into in every single event, okay? And so since it's not kind of a properties of individual particles, but it's really a collective phenomenon, this is why this is called collective flow. Okay, so the first thing one should ask oneself is, why is there, I mean, we're colliding nuclei, right? Nuclei sort of, could be thought of in the simplest idea as sort of round blobs, okay? So why is there preferred direction, okay? And so clearly, if we collide the nuclei not head on, but with sort of an offset here, yeah, then with a finite impact parameter, then there is a preferred direction, which is given by the direction of the impact parameter, okay? So that's clearly something that can give us a preferred direction, but actually the situation is even kind of more subtle than that, okay? Actually, if we think of a nucleus, then the nucleus is not just a round blob, right? But it consists of nucleons, and even nucleons have their own substructure of quarks and gluons, okay? And so in every collision that happens, essentially there can be large fluctuations of where the position of these nucleons is. Yeah? So a better picture of how an event happens is that in each nucleus we have nucleons, okay? And when they collide, then individual nucleons hit each other, they deposit some energy, okay? And this is giving rise to fluctuations which essentially break every symmetry that we had in the transverse plane, okay? So if you look at this central cartoon here, then the kind of the pink blobs and the blue blobs are supposed to indicate the positions of the nucleons before the collision, and then as they have collided, they leave this blue shaded region of where the energy was deposited in the transverse plane, okay? And there are large fluctuations. Now, this is some kind of asymmetry that we have, okay? But it's an asymmetry that we have just in the initial state, so just after the ions have collided, okay? And that somehow has to be translated, or there's got to be a way that this translates into then the anisotropic motion of the particles that we see produced at the very end of the reaction dynamics, okay? And so the way we understand this is that this initial energy starts to expand into space, okay? And this expansion into space is what converts this. I mean, if you take some shape and you expand it, right, then the anisotropy in coordinate space will be expanded into, will be translated into an anisotropy in the motion in space, okay? So the expansion dynamics of this plasma, of the quark-gluon plasma, is actually what converts the initial spatial anisotropy into anisotropic flow of particles in the final state, okay? And this is what we measure in terms of this collective flow coefficients that I introduced here in the previous slide, okay? Now, the interesting thing about this is that, of course, the way this happens in detail, okay, so how efficiently, for instance, this initial anisotropy is converted into final anisotropy is again something that depends on material properties of the gluon plasma, okay? And so that actually is something that contains information about how this whole reaction dynamics happened, okay? And that is very similar to, for instance, if you look at the anisotropy of the cosmic microwave background, right? The cosmic microwave background is also something that we observe today, okay? Yet it can tell us something about the evolution of our universe. And so in a sense, when we study collective flow in heavy ion collisions, we're doing a very similar thing, okay? We're looking at anisotropies of the particles that are produced at the very end, and thereby we try to learn something about the way the reaction dynamics took place at much earlier instance of time. Okay, so how does this look like? So in principle, this is sensitive to kind of a number of issues. Okay, so what we measure at the end is this anisotropy of particle motion. Okay, well, that depends essentially on two things. It depends on sort of how anisotropic was our initial state to start with. This, so you can just quantify some initial state eccentricity. Okay, and it depends on the expansion dynamics, which itself will depend on material properties of the QGP. So, for instance, if you take, if you say you were to do this such a type of experiment, say you take some blob of matter, let it expand. You do this with I don't know, spilling coffee. Okay, then coffee spills very different than if you were to spill, for instance, honey. Okay, and so it all depends on the properties of the matter that you study. Okay, and so what calculations show, okay, and I'll tell more about this. So that's kind of then the main theory part, really, is that the way that actually this happens in heavy ion collision is a very, very efficient conversion of this initial state eccentricity to momentum anisotropy. Okay, which requires the quark gluon plasma to behave like a very, very fluid. Okay, so we call this an almost ideal fluid, which means it's a fluid that has very little dissipation in it. Okay, and so essentially one of the big achievements in heavy ion collision is that by kind of doing a statistical analysis of the measurements of these anisotropies that you have, okay, you can then really extract material properties such as the equation of state or transport coefficients by comparing theoretical models to experimental measures. Okay, so my plan was to now then walk you once through this, so kind of how we do this in theory, so how we actually describe the reaction dynamics. I don't know if there are questions on kind of just the basic phenomenology that we should take now, or everybody fell asleep. I don't know.
I have a question. So you were just now saying that the quark gluon plasma behaves like an ideal fluid.
Mm-hmm.
I was wondering about like things like viscosity. This is, I guess, something people think about. And
yeah, absolutely. So viscosity. So how do you learn it's an ideal fluid? You study the effect of viscosity, okay, and you see that your observations are incompatible with having a very large viscosity. That's actually what you learn. Yeah.
Yeah. So that was my question. So
yeah.
That viscosity is very small.
Yeah.
Right.
You're saying that because there's a smooth transition from eccentricity to the final state momentum anisotropy, that implies that the viscosity is low.
Yeah.
Why?
It's a very efficient conversion. That's what I'm saying, right? If the viscosity was large, the conversion would not be efficient, and then it wouldn't be compatible with observations essentially.
But is there perhaps like some way I can think about why the conversion being efficient would imply that the viscosity was low?
You want a simple way to see this? Well, I mean, imagine, so go back to the coffee spill example, right? If you spill coffee, you know, it will give you all kinds of crazy patterns. Coffee is water, basically has a small viscosity, okay? If you do this with honey, honey has a much higher viscosity. And honey will kind of spread more isotropically, essentially, because, I mean, will evolve much slower and everything, okay? And so it's essentially the same phenomenon that's at work here. Yeah? So what viscosity does is kind of, it blurs everything out, okay? And thereby you get less sensitive to kind of these small ripples and structures on these small scales. Yeah?
So would that mean that processes happen relatively fast in a quark-gluon plasma?
Yes, essentially yes. Yeah. I think you guys are asking a lot of questions that already kind of go towards the next part. So maybe we should go on, okay? Because what I was planning now is to walk you once through the full theoretical description of a heavy ion collision, okay? And I think you are. I think your questions are kind of sort of relatively advanced, maybe more advanced than I would have expected them to be at this point. Yeah. Okay, good. So, but again, I mean, feel free to interrupt me if you have questions, right? So otherwise, I'll keep going and we will talk more at the end. Okay, so let me once walk you through. So what have we seen now? We've seen, okay, heavy ion collisions. We can learn interesting things from them, okay, but they're also incredibly complicated because, you know, we have very little control. We can only measure at the end, okay, and from that we need to calculate back, okay. So we need a good description, a good way how to describe this. Okay, I'll skip this. And well, no, I'll actually say this, okay. So first thing we need is we need good coordinates to do this. So I told you that for momentum measurements, we use these boost-friendly coordinates, basically because it's an approximate symmetry of the system, okay? And actually, we do the same thing when we study where things are in space, okay? So you can do the analogous transformation for just spatial coordinates. You use instead of using the z direction, you use so-called space-time rapidity coordinate, which combines time and longitudinal direction, so longitudinal direction along the beam. Again, this is something that's additive under boost, so you expect things not to change much as a function of rapidity, okay? And then to kind of look at the system, to properly look at the system as a function of time, you want to have a time that's invariant under boost in the longitudinal direction, okay? So you use the proper time in the longitudinal direction, which is just root t squared minus z squared, okay? And so if you assume that this is an exact symmetry of boosts, essentially, then you can basically go down from 3+1 dimensions to 2+1 dimensions and only study depends on proper time and position in the transverse coordinates. And usually when I show you these 2D plots, like of the energy density or so, that's actually something that people assume. I mean, by now people do these calculations also in 3+1D, but to kind of, I mean, to understand the phenomena, it suffices to be in 2+1 essentially. Okay, so how do we then think of heavy ion collision? And so in principle, I told you, okay, look, right? I mean, this is physics of strong interactions. We know QCD, okay? And so in principle, we should just try to take QCD and solve it, okay? And calculate what goes on in a heavy ion collision, okay? Problem is this is not possible, okay? So studying real-time dynamics in an interacting quantum field theory is essentially impossible. We just simply don't have theoretical tools to do this. And so what we do instead to study heavy ion collisions is we use a hierarchy of kind of effective theories of QCD, okay, to describe different stages of this reaction dynamics, okay? And, okay, so how does this look like? So essentially before the collision, what we have is we have atomic nuclei which collide. So the way we describe them is we describe them of the atomic content of atomic nuclei, and then we study the way that these two interact and deposit energy when they collide. Okay. After that, what actually happens is that at high energies, the nuclei mostly pass through each other, and we're just left with the chunk of energy that they deposit. Okay, so from this first slide, and the time that it takes them to pass through each other is insanely short. It's a very tiny fraction of 1 femtometer divided by the speed of light, so 1 Fermi over c. That's the unit here always, and that's very short in the time scale of the overall reaction dynamics. So after this first slap, okay, we're basically left with this highly excited state of matter. This is a very violent reaction. Okay, so we should expect a system which is sort of far from equilibrium. But then, and that'll be essentially the topic of next week's talk to some extent, then over a short period of time of 1 Fermi, the system actually starts to thermalize, okay, undergoes some non-equilibrium dynamics, such that by about a Fermi over c, we have close to equilibrium QCD matter, so close to equilibrium quarks and gluons, okay, which we can then describe using another effective theory, yeah, namely an effective theory that's close to equilibrium, which is hydrodynamics, okay? So then you have this blob of matter. You have a blob of matter in empty space. What will happen is, well, this blob of matter will expand into the empty space, okay? You do that using the laws of hydrodynamics, but if you expand energy, I mean, if you redistribute the energy into a larger volume of space, the system will cool, okay? So in the QCD phase dynamic, we will go down in temperature, okay? And until at some point, we reach these transitions where quarks and gluons can no longer roam around, okay? But they have to reconfine into hadrons, okay? So at some point, there's a transition from quark-gluon plasma to the hadronic stage taking phase, okay? That's kind of, that takes about, so that happens after about, say, 10 Fermi or so for large nuclei, okay? But then the hadrons that are produced, okay, they can still interact and scatter with each other before eventually they fly into the detectors where they're actually being measured. And so, so that's at the very end is when we do the measurement, okay? And what we really want to learn about is mostly this green phase. Well, okay, learning about the blue phase would actually be even more exciting if you ask me, but that's even more difficult because it's at the very beginning and very short, okay? So the way that this is done in practice is actually, you kind of do it exactly like this, okay? So you have these different effective descriptions for these different stages, essentially, and in practice, one then has a multi-stage evolution model where there's a particular model for the initial state. There, you can have some connections to fundamental QCD by basically really saying, okay, I take QCD structure of nuclei, I calculate QCD cross sections for the interaction and how the energy deposits, and then take that, okay? Then there's a module for the non-equilibrium dynamics. This I'll talk about more next week, okay? Then there's fluid dynamics, okay? Fluid dynamics needs to be then converted into particles, and particles undergo rescattering of hadrons, and then you follow this whole pipeline and really then compute observables as they are done in experiment. In addition, heavy ion collisions, so I'm only talking about kind of the mainstream here. Okay, these are really multi-messenger experiments, so you can also study unusually highly energetic probes. So this would be jets, right? That's something that Will does a lot. Or you could study heavy flavor hadrons, so not just the normal production of normal pions or so, but the things that contain heavier quarks. Or you could study photons or so. But then typically this is something that goes on top of this with the own physics, but has kind of, so this is the physics of the bulk of, say, 95% of the energy that goes into a heavy ion collision loss. Good. So let's have a little bit of a look at that kind of this individual, the way that this works, okay, individually, okay? And so the first thing you need to do is you basically need to describe when two nuclei collide, okay, how much of their energy, how much of their momentum, and how much of their charges, okay, they lose when they go through each other and deposit into kind of the central region where the fireball remains, okay? Okay, doing this dynamically in QCD is hard. There's, again, no real way, so there's kind of different ways you can approach this problem, okay? The simplest way people have done this for a long time is that they essentially just have some parametrization for what happens, okay? So you can say if any nucleon collides with any other nucleon and they overlap like this, at a given energy or so, then this will lead to this and this amount of energy with this and this fluctuations, okay? And so these are type of parametric models, okay? The advantage of this is essentially that, okay, you say, good, it's not, you know, it's no fundamental theory behind this, but you kind of can quantify your uncertainty, right? So you can vary your model parameters very easily and so forth, and sort of give it an uncertainty that you propagate into fits that you do to data. Okay, you can also use effective models. So it's the blue here, okay? Where at lower energies, you would say, well, okay, good. I mean, this is protons and neutrons scattering, or protons with protons. I know how this happens. This is a problem in hadron physics, okay? And I try to model this and extrapolate this to higher energies, okay? Or you can really try to do this kind of more microscopically in QCD, so scattering of quarks and gluons inside nuclei. Then you have to know about the distributions of quarks and gluons inside nuclei and how they interact with each other, okay? And that's so that are these sort of that's what's called saturation models typically in this context. So an example would be IP Glasma model. Maybe you have heard about this or not. Now, this gives you the initials. So no matter what you do, what you will end up with after this is you will know how much energy, momentum, and charges are distributed in your fireball, okay, at the initial state, okay? So kind of right after the collision. And then you want to know how this evolves towards equilibrium. I'll say more about this in the next week, so stay tuned, okay? Now, once you have this, okay, you want to, I think I already said this, you want to, you can use another effective theory, which now avoids, which now takes advantage of the fact that your system is close to equilibrium, okay? And that theory is hydrodynamics, and that's a really nice theory, actually. Okay, it's a really nice theory because it kind of makes a minimal set of assumptions about what is the properties of matter that you have. Okay, so it's a universal. So in that sense, it's a universal theory. Okay, for macroscopic properties of any kind of many-body system. Okay, and it's based on two things that you assume. So on the one hand, you have conservation laws. You have conservation laws for energy, momentum, and charges. So that's something that nobody doubts. So that's so energy is conserved in QCD. The charges are conserved in QCD. So that's where things are very safe. So you can express this through the conservation of the energy momentum tensor. So the divergence of T mu nu is 0. Okay, so T mu nu is the energy momentum tensor. Okay. But so if you count this, then T mu nu would be, so this would be a symmetric rank 4 tensor. So this would be a 4 plus 3 plus 2 plus 1 degrees of freedom. Okay. But D mu T mu nu is 0, is nu is the free index. So you only have 4 equations for 11 components. So that's not closed. So you need additional information to close this set of equations. Okay. And the idea is that in hydrodynamics that, okay, what you do is you systematically expand around thermal equilibrium, okay? Because in thermal equilibrium, you know that there are exactly 4 degrees of freedom that describe the energy and momentum content of your system. Namely, in equilibrium, there would be a temperature and a velocity in which your system moves. Okay, so T and U mu would be 4 velocity, so but actually only has 3 independent components. Okay, and so the idea is to organize this in an expansion around equilibrium, where you say, okay, at first order, I assume my system is always in equilibrium. Okay, but then I systematically take into account deviations from equilibrium, which in this theory happen due to the fact that the system is dynamically evolving and that it's not smooth, so to say, in space, not smooth, not uniform in space. Now, theoretically, this is nice, okay? But what one should say, okay, is that, well, what are the downsides? So the advantage here is you treat it macroscopically, okay? And you expand in things being slow and smooth, okay? Now, in reality, of course, the heavy ion collision is not truly that macroscopic. It's also not truly that slow and smooth. Okay, so one is really pushing this theory also to its extremes. Okay, and in fact, one of the big questions in the field is sort of, you know, how far can you push this? If you sort of make the go from heavier ions to lighter ions, make the system smaller and more shorter lived, and this is something I will address next week. Now, what does this theory give us, though? So, in a sense, I already said this. So let's look more at kind of just the simplest way that this could work. Okay, just for an ideal fluid. Okay, so so an ideal fluid refers to the fact that I treat the system as if it was in equilibrium at every point in space and time. Okay, and then the energy momentum tensor is simply given by the energy density and the pressure. So the energy density is the time-like component of the energy momentum tensor, and the pressure is kind of is the space-like component. So the way you would write it is written here on the left, where u mu is the rest frame velocity of the fluid. It's normalized to 1, and the pressure is given as a function of the energy density determined by some equation of state. Yeah, and so if you combine the conservation laws, so conservation of energy and momentum, with the constitutive relation. So the constitutive relation saying that the energy momentum tensor is that of an equilibrium system. Really what you get is you get 4 equations of motions for 4 fluid variables, namely the energy density and the velocity of the fluid. Okay, so you can in principle rearrange this a little bit. I think, okay, I'm going to send you the slides, right? So if you want, you can look at this more. So you can insert this. You can project you can project essentially along the flow velocity, and you can project transverse to the flow velocity. If you project along the flow velocity, that's shown here in the top, okay, what you get is you get an equation for how your system kind of locally cools. So D is u mu d mu, so this means the time derivative of the energy density, and that's equal to the energy density plus pressure times the expansion rate. And so you get one equation which describes you how your energy density cools due to the fact that it's how the system cools due to the fact that it's expanding. Okay. If you project transverse to the flow direction, okay, what you get is you get this equation down here. And that is actually the one that's kind of relevant for understanding collective flow. Okay, what you get there is you get something which is in principle very analogous to Newton's second law. Okay, so you get something, namely E plus P multiplying the time derivative of the velocity. The time derivative of the velocity is the acceleration. Okay, and the acceleration of the fluid happens due to gradients of the pressure. Okay, so what this means is, so gradients of the pressure are like a force, okay, that leads to acceleration of the fluid, okay, and the moment of inertia, which is the mass, is given by the energy density of the pressure. I think it's related to the enthalpy, okay, and so this is then what really in hydrodynamics generates the collective motion of the fluid. So if you look on the left at this initial state, then you see you have hot spots and you have cold spots. The higher the energy density, the higher also the pressure. Okay, so you have gradients of the pressure as indicated by these red arrows. Okay, and so what it means is if the pressure gradient goes outward, okay, this will accelerate the fluid in that direction, okay, and so starting from this initial state on the left, if you evolve it for some time, this will transform this into the collective motion of a fluid. Okay, now, of course, this is not the full story, right? Yeah, so this would, because now what we assumed is that the system is at equilibrium in every point in space and time. Yeah? But of course, the system is evolving. It's only short-lived, so it will never reach equilibrium quite yet. And even if it was to get there, because it's moving fast, it will be driven out of equilibrium. Okay, and so basically, what you then have to study is you have to study corrections to the energy momentum tensor that you can include. Okay, so And that's actually an interesting, exercise to do kind of by itself, okay? Because it's not so clear how to do this for a relativistic fluid in general, okay? So if you look at, so what you can do is you can kind of do a more general decomposition of the energy momentum tensor where you just say, okay, let me take something that I call the fluid velocity, okay? Let me take something I call the energy density, something I call the pressure, okay? And I write down just the most general decomposition of a symmetric rank 2 tensor in this, okay? Then you'll find out you can always do this, okay? But you need to find equations that close or they tell you what is now the energy density and what is actually the velocity I associate with a given energy momentum tensor. And so typically the way this is done is that one says, okay, the energy momentum tensor is essentially the direction in which energy, the fluid velocity is the direction in which energy flows. So what one would mean, this would mean one would use this kind of Landau frame definition. So this is the time-like eigenvector of the energy momentum tensor, but basically physically what it means is you tie the fluid velocity to the energy flow of your system. However, it turns out this is actually not so advantageous because the theory that you end up with is actually not causal and not stable in this case, at least if you only go to leading order in gradients. Okay. There's a way to cure this by not tying it directly to the energy density. There's some interesting recent work on this, okay? But the typical way that this is actually fixed is to say, well, okay, maybe it's not stable and causal because I'm telling my system to kind of instantaneously respond to certain gradients that it has in space. Okay, and so the way that this is typically cured then is to say, well, okay, I don't tell that the response is instantaneous, but I tell my system to relax to the typical to relax to the response that they want to have on some time scale. Okay, and this restores these issues of causality and stability. And so this way one then recovers what is known as ordinary first-order fluid dynamics. In first-order fluid dynamics, one essentially has two deviations from equilibrium one can have. One can have the response to shearing the system, okay, and one can have the response to compression, okay, which will change the pressure locally, and these are parameterized by the shear and bulk viscosity of the system, okay. And so these are transport coefficients. So these are dynamical material properties of the system, okay, and that will then affect the expansion dynamics. Good. And so this is something in principle. So in principle, again, these transport coefficients could be something we could calculate in QCD, but again, this is a very, very hard calculation. And so instead, what we try to do is we try to determine now how perfect is the fluid essentially. Yeah, so how large are these dissipative effects by running our models and comparing to experiment. Okay, then I should also soon come to an end, I guess, right?
Slowly.
Huh? Yeah. Okay. So I'll say a little. I think I have about, I don't know, 8 slides left or so. Yeah. But okay. Good. So this is essentially how you do fluid dynamics. Okay. So in the simplest case, you solve ideal fluid dynamics, but then okay, you want to account for corrections from gradients, so this makes the fluid dissipative. Okay. But then what really happens is that okay, your fluid expands. Okay, it cools, and at some point, the quark-gluon plasma will have to reconfine into hadrons. Okay, so at some point, quarks and gluons can no longer exist in the plasma; they'll have to rebind. Okay, and well, we know that this happens at a temperature of 155 MeV, roughly. Okay, the thing is that once you have these hadrons and they also fly out, okay, they'll become less and less. I mean, they'll become more and more weakly interacting, okay? But these interactions is what is needed to restore proximity to maintain proximity to equilibrium. So when the system stops interacting, at some point it will fall again out of equilibrium, and then you can no longer use hydrodynamics to describe it. So at late times, okay, we again have to stop with our hydrodynamic description, and we have to transition to this particle-based description of the particles that are produced in the reaction and that then essentially fly non-interactingly to the detector. Yeah. Now, probably the biggest and biggest unsolved mystery in this whole description is how do quarks and gluons recombine into hadrons at the sort of towards the end of the reaction dynamics, okay? And the honest answer to this is we have absolutely no clue, okay? Yeah. But the good thing is we have a way to model this, okay, which is still theoretically sound, okay? The reason is that, okay, well, if you assume that this happens in equilibrium, okay, then it's actually simple, okay? Because if the system is in equilibrium, okay, then you just know, okay, good, the hadrons I produce should be what the hadrons that appear in the equilibrium partition function of a hadron gas, or you have an interacting system of hadrons, okay? Typically, one doesn't make this an interacting system of hadrons, one make this a non-interacting system of hadrons, but one really resorts to this statistical description, exploiting the fact that when this happens, one is somehow close to equilibrium. And then basically what you can do is you can look at your collision, you can look when sort of your collision volumes or when different regions of the collision reach this temperature of the confinement transition, so when hadrons are formed, okay? This defines this indicated in red space-like hypersurface, so space-like surface in the four-dimensional space, and you can study then the flow of energy and momentum through that hypersurface, okay? And you equate that to the energy and momentum in a hadron gas, yeah, so in a gas of hadronic particles, okay? And by this you can then basically just calculate their abundances, yeah, at a given temperature where this happens. Now, this is what you would do for an ideal fluid. Things can become a little bit, so if the system is not actually in equilibrium, but it's sort of slightly out of equilibrium when this happens, okay? Then you have to account for corrections to that. And then that is a much more complicated story, okay? But in principle, we don't have to address the way that this happens dynamically, but we do it again on a statistical way. And this way we can convert the QGP fluid into particles here. Yeah. Perhaps worth noting that this is done usually in a grand canonical way. So actually what you do is you only conserve energy and momentum on average, okay, but not kind of cell by cell, so to say, locally. Okay, good. And then so the final step that you have to do is you basically simulate how the hadrons produced evolve further. They can still meet and scatter, okay? And so for this, essentially what you do is you just ballistically propagate them to the space, okay? And then when they meet each other, you collide them. So this would be described by a Boltzmann transport equation, okay? And there are codes which simulate this. So you see here, for example, I think it's a relatively low energy collision where here kind of these bubbles are hadrons. So after 20 Fermi, they're still relatively close together, but then they move further and further out, okay? And eventually you would do this until no further interactions take place. And then that's what you can equate to the measure. Okay, so that is then essentially everything you need to do to describe this. Okay, so now how do you learn something about this? So in this whole business, there's a lot of things you don't know. Okay, and so kind of the take one does is that one tries to parameterize the ignorance. Okay, so in these models, things you don't know are things about the initial state. So how is energy deposited? There are things you don't know, like these transport coefficients. So these are things you actually care about, right? So what are material properties of the plasma? Okay. There are unknowns related to hadronization. Okay. And that's about it. Okay. There's also unknowns to know about how the system thermalized. Okay. So typically there's on the order of 10 to 20 unknowns. And the idea is then, okay, you vary all of these simultaneously, okay, and you try to get the best fit to data, of course, within things that are, reasonable theoretical expectations. So you look at all the observable properties that come out, okay? And compare this to data, and what you get is then some kind of fit matrix like is shown here on the red, okay, which shows you 20 parameters in some, I think these are 20, yeah, or 16 in some analysis, and sort of contours show which parameters are likely or not. Yeah, so the darker, the more likely, and you see some of them are correlated with each other and so forth. Okay, and really the most unknown ones are things that relate to the initial state, okay, and things that relate to transport properties. But okay, from this you can then learn. First of all, you can learn something about properties of the quark-gluon plasma. Well, first of all, you should say that, okay, what you can actually, if you tune your models, you can actually get a good description of the data. So if you look on the right here, this shows results from lead-lead collisions, left column, and then gold-gold collisions, LHC and RIC on the left and right. Okay, top is something like just total number of particles produced, always as a function of this centrality. So head-on collisions on the left, more peripheral ones on the right. Okay. Second row is average momentum. Third row is this anisotropic flow. So these VNs. Okay. And then the lowest row, which is only for LHC, is some kind of fluctuations of the average expansion motions of the average transverse momentum. And you see, okay, if you tune your model, then indeed you can basically describe all this data really to a remarkable degree. Okay. However, okay, to get this level of agreement, okay, you need to describe the right material. So you need to describe the quark-gluon plasma correctly. So for instance, you do get constraints on what your transport properties are. Okay, and so really what quantifies the dissipation in the system is not the viscosity itself, but it's actually the ratio of the viscosity to the entropy density. Okay, and so this is what you see in these left two plots. So the light gray bands here show you kind of all the space of possibilities that was considered in the analysis. Okay, and then the darkest blue is the 60% confidence level inference that you get from comparing to data. So if you take the data and you say, okay, and the 60% confidence level, I would then extract that actually this shear viscosity to entropy is a very small number. So it's orders of magnitude smaller than it would be, for instance, in water or so. And likewise, also the bulk viscosity is very small. So at high temperatures, we expect it to be very small theoretically also. But even in the vicinity of the transition region, it's also not huge actually. Yeah, okay. I think that's that's everything I had prepared for today. Okay, so I thank you for your attention.
Okay, thank you, Sören, for that nice introduction. So, do we have any more questions left from the students? Yes, Daniel?
Yeah, I was wondering, so we're going through all these different effective models to try and get a picture of this overall process. How do we determine when we swap from one model to the other? Is that some kind of parameter that we can include in our fits, or do we have a theoretical description? What's the...
Yeah, that's an excellent question, actually, right? So in principle, okay, or ideally the way this should be built is that the different effective theories have sort of overlapping ranges of validity, okay? And then it doesn't matter when I switch from one model to the other, yeah? And there's cases where this, so let's just go back here, right? So, yeah, so that's actually what I tried to indicate here, right? So for instance, if you use, so say you switch from non-equilibrium dynamics to hydrodynamics, right? That at some point the system becomes close to equilibrium, and hydrodynamics, at least dissipative hydrodynamics, also works slightly away from equilibrium. And then there's a range where the matching is insensitive, okay? And so for instance, for this transition, if you do this properly, you can do it like this, and then it doesn't matter at what point you match, yeah? Oftentimes, this is not done in the analysis, yeah, So for instance, also for switching from the fluid to hadrons, okay, it's very difficult, okay, because there we don't really have, I mean, the dynamical descriptions don't really match to 100%, okay? And then indeed you do exactly as you said, you include it as an open parameter, so to say, in the model, and you try to determine what works best, but also take into account the uncertainty that comes from that. Yeah.
All right, thank you.
I also had a question. You were talking about non-equilibrium corrections, and I wondered if you could give an example on you were talking about these different types of ansatz that are used. Could you give an example?
Example for what exactly? Sorry, I missed that. So I think this was in the context of fluid dynamics, right?
Yeah. You were talking about non-equilibrium corrections, and there are these different ansatzes used to correct your models. And I wondered if you could give examples for such ansatzes for corrections.
Yeah, so in principle, okay, so in principle, so the way you organized this, so I was a little bit fast here because I was noticing I was going out of time. Right? So the way you organize this is you say, okay, I have my energy momentum tensor, okay, and I know in equilibrium I can define it through thermodynamic quantities, namely the temperature and the fluid velocity. Okay. Now you know what the system, what will drive the system out of equilibrium, okay, is the fact that the system lives for a finite time, and that the system, if you put two cells which are adjacent to each other at different temperatures, right, that's overall a non-equilibrium situation because energy would want to flow from the higher temperature to the lower temperature. So this will also cause something, okay? So what you do is you organize these corrections. So you say it's an equilibrium part plus a correction, and you organize these corrections in gradients, okay, of your thermodynamic variables, namely temperature and the fluid velocity. Okay. So what you do then next is you write down all possible tensor structures essentially, right? So there's scalar gradients, there's vector gradients, there's tensor gradients, and so forth. Yeah. And you look what tensor structures can contribute. Okay. Then basically you end up with this here, okay? So you have unknown quantities that are in there, and now you find a way to close this in terms of gradients. So for instance, you could say, okay, the heat flux, right? This is a vector, so this could be a gradient of the temperature, or actually of the inverse temperature you would take, yeah? Okay? But it turns out this is an effect you can eliminate, yeah, by saying, okay, I just follow the flow of the energy density, yeah, then this kind of, what I described before with the two thermal boxes is heat conduction, yeah, then you just say, okay, heat conduction happens to fluid motion, yeah, okay, and yeah, so that's essentially how it works. And an example is the part that then remains essentially would be for instance here would be the easiest probably to understand the bulk viscosity actually. Yeah. So if you look at the general decomposition of the energy momentum tensor, there's something that looks like the energy density, something that looks like the pressure. Now you say, okay, the energy density is something I know, okay, by following the energy flow. Then I say, okay, I know the energy density, I know the velocity, but then the pressure doesn't have to be the thermodynamic pressure. It could receive a correction, okay? It could have received a correction from a scalar gradient, and the Euler scalar gradient you can form with one derivative is the divergence of the velocity, yeah? And then you put a coefficient in front of that, and that happens to be the bulk viscosity, yeah.
Thanks.
None from the students? No.
We went through that one so often that
Yeah.
Well, okay, let me ask an embarrassing question. All right, so on like slide 1, you talked about the chiral phase transition. And
where is it here?
well, no. So
Want me to go back to slide 1? No, slide 2, I think.
maybe 2. So yeah, exactly. So you make this statement that I always make when we always all make, which is that QCD is associated with the 99% of the mass of the observable universe because it's the mass of the nucleons. And I mean, certainly, you know, the fundamental degrees of freedom quark gluons are massless. So how do I think about this mass generation, especially in the context that the nucleons are bound states? So normally we think about bound states as having some kind of negative energy from the fact that they're bound. So how do I think about this creation of positive mass from this bound state?
Well, I mean, one way to think about it, I guess, is that you think that that if you have a quark or something like this, right, that you think of it more as a constituent quark, right? So that it's not just a bare quark, but it has a gluon cloud around, right, and it has energy attached, or there's energy in the gluon fields that bind the nucleons together. Yeah.
Yeah, but I mean, again, so coming back to, if I think about the hydrogen atom, right? So the hydrogen atom is the mass of the proton plus the mass of the electron minus the binding energy. So the fact that the proton has this electron that is dragging around actually decreases its mass rather than increasing it.
But there's not the energy in the, right? I mean, you don't have like a gluon flux tube in between, right? Which makes up the energy, right?
You might have some kind of photon flux tube.
Not really. I mean, you're essentially talking about the same degrees of freedom, right? You're talking about your nucleus and your electron, say your hydrogen, proton and electron, and they're not dressed terribly widely, right?
Right.
If you talk about these guys,
yeah.
you talk about a vacuum condensate, right? Or flux tubes, whatever. I mean, whichever way you use to describe this. So there is, right? On the distance scale of the hydrogen atom, the vacuum polarization clouds don't matter terribly much. They're kind of smallish.
Okay, so I guess you're saying, all right, so there's some kind of symmetry breaking that says I'm not really dealing with quark gluons, I'm dealing with some other non-perturbative objects that I don't see in my QCD Lagrangian. Those things have a mass.
Yeah.
And the fact those are bound, then if I add those masses up, then the mass of the proton is smaller than that.
Yeah, right. I mean, if you do NGL models for the kind of symmetry breaking, you kind of get the 300 MeV things, right?
I'll take your word for it.
But that's, I mean,
especially you.
I mean, at the end of the day, it's a picture, right? I mean, I think if you want to look at this, maybe a little bit more seriously, then one should also take kind of these constraints that come from gravitational form factor. I mean, you can try to split this into kind of different contributions which make up the mass, right? I mean, so this is in the context of what you do with gravitational form factors, right?
Would that be helpful? Because that's usually thought of in the context of deep inelastic scattering, right? So you're back in the sort of high Q squared perturbative picture.
Yeah, but I mean, look, right? I mean, if you look at the trace anomaly of this, right, then that's basically the mass of the nucleon, right? And so you can then study kind of the contributions of different operators to that. So there's people who address this on the lattice.
Yeah, and
there's somebody who's really kind of
for me, like I should do this.
Nobody has an absolutely watertight quantitative answer to this, right? Other than the lattice QCD people, if their continuum extrapolations are good.
Yeah, but then also, right? I mean, then you get the answer, but you don't really have a dynamical understanding, right? I mean, other than saying this is the answer, right? So.
So Soeren at Bielefeld is contractually obliged to say the last exactly what's going on, right? Cool, thank you.
Okay. Well, then it's my turn to ask a question.
Chair's prerogative.
Okay, so Soeren, at the end of all of this, then I imagine your output is that you want to plot presumably these trajectories in your QCD phase diagram, right? But if you carry out all this whole simulation from the initial state or through the end, you should be able to get a trajectory somehow, right?
Yeah, you do. Yeah, you do. And I mean, actually, what you get, I mean, I don't have a plot of this, right? But I mean, so, okay, so here this, right? So these trajectories you can actually put, if you run the system, you can put actual points. What you get is not sort of a point, but you get a cloud, right? Because every point in space and time of the collision sort of, or every point in space at a given instant of time is sort of different in the collision. In fact, if you move kind of closer to the beams, you also get to higher densities because some of the baryon charges is deposited sort of more there. And yeah, I mean, you do get this at the end of the day. Yeah. What limits this to the upper end is of course that the system takes some time to reach proximity to equilibrium. Yeah? So it's I mean, there's also simplification in here, right? I mean, this is an equilibrium phase diagram. The system we have in heavy ion collision is kind of always evolving, right? So it's never really strictly in equilibrium, so to say. Yeah. Yet, I mean, we use hydrodynamics, okay? So it seems to be a reasonably good description.
Okay, so good. So, but I get that at the end of this, what you should then know is yeah, this trajectory though. But and you compare that to experiment, right? So how do you use that to then find out whether you've gone across a first order phase transition or you've the critical point, right?
Yeah, I mean that's an excellent question actually, right? I mean, there's different things. I mean, there's different things. I mean, different observables that people have speculated about. You know, where I mean, what happens if you go to the first order phase transition is, I mean, you have a change in the equation of state, right? So you should see the difference in the equation of state, and there's different observables that should respond to this. One example would be anisotropic flow. I mean, so there is things in anisotropic flow where you could see this. Okay, there's also observables kind of tell you a little bit about how quickly the expansion took place, and you would expect that the expansion kind of stalls a little bit more at this stage, and you would see this. But yeah, I mean, in the end, it's a little bit in the details. I mean, look, right? I mean, we haven't found this, right? So it's so in that sense, we don't know, right? Yeah.
Yeah. Okay.
Yeah, I mean, for the critical point, it's also very tricky, okay? Because I mean, actually, if you draw a critical point there, I mean, so this I know more about, so I can tell a little bit more. So you put a point there, right? And you say you shoot the system at the critical point. What will actually happen is, because at the critical point the dynamics become so slow, the system will fall out of equilibrium before you hit the critical point. Okay, then it becomes a question of how fast you go there and how close to the critical point you fall out of equilibrium that you can see. In that case, you can, I mean, there's things you can control, and you could, in principle, think about establishing a protocol with which you find this. But in principle, also the question that you ask is a very interesting one. Yeah, I mean, how do you find a critical point if you can just fly by and you cannot prepare the system there statically?
Okay. All right. Yeah. Thank you. I guess you've exhausted everyone here.
Pretty good.
Yeah. Thanks, guys. Next week I'll be on time.
Yeah.